Today's lesson is on practical transformer equivalent circuit. In this lesson, you will study how the equivalent circuit for a practical transformer is developed. The learning outcomes for this lesson are to identify the losses in a practical transformer and to develop an equivalent circuit for a practical transformer. We start with an ideal transformer where there are no losses. This transformer will contain a primary winding where the time varying voltage source is applied, a secondary winding to which an external load is connected, and a magnetic core which couples the magnetic flux from the primary side to the secondary side. As you can see in the figure, there are NP number of turns on the primary winding and NS number of turns on the secondary winding. This slide shows you the circuit schematic of the ideal transformer. If you now compare the ideal transformer with the practical one, the practical one will have losses due to the leakage flux, losses in the windings, and will require a current to magnetize the core, and also losses in the core. All these losses have to be taken into account in developing an equivalent circuit. Let us therefore look at these losses one by one. Let us first look at the flux leakage from the core. Due to imperfect coupling between the windings and the core, there will be some flux leaving the magnetic core. This flux is called the leakage flux. This happens both at the primary side as well as the secondary side, even though the figure in the slide only shows you the primary side of the transformer. The total flux at any side of the transformer can be written as phi is equal to phi m plus phi l, where phi m is the mutual flux which travels through the core, and phi l is the leakage flux. Now, if you differentiate this flux equation with respect to time and multiply by the number of turns n, according to Faraday's law, this gives us a voltage. Vt is the total induced voltage. Et is the induced voltage due to mutual flux, and ELT is the induced voltage due to leakage flux. We also know that if there is an inductor with n number of turns with flux phi, inductance L, and current I, we can write N d phi over dt equal to L di over dt. Therefore, we can express the voltage due to the leakage flux by an inductor in our equivalent circuit. Since we have leakage flux on both sides of the transformer, we can indicate this by two series inductances added to our ideal transformer model. Let us now look at the losses in the windings. These losses are due to resistances in the windings. Even though transformer windings are made out of very good conductors like copper, they still have some resistance. These resistances can be represented by series resistances on both sides of the transformer. The primary side resistance is represented by Rp and the secondary side resistance by Rs, as shown on the slide. Next, we will look at the magnetizing current. Even when there is no load connected to the secondary side of a transformer, it still takes in some current. Part of this current goes to magnetize the core and is known as the magnetizing current. This current is in phase with the flux, but 90 degrees out of phase with the induced voltage. This effect can be represented by a shunt inductor because we know that current lags the voltage in an inductor by 90 degrees. This slide shows you the circuit with the shunt inductor Lm included. Finally, we come to the losses in the core. Core losses are two types: hysteresis losses and eddy current losses. The hysteresis losses are due to the cyclic magnetization and demagnetization of the core. The BH curve shows this process, and the power loss is proportional to the area enclosed within the loop. This loss can be minimized by selecting a material with a small loop area for the transformer core when designing transformers. For example, silicon steel is widely used in transformer manufacture. The second type of loss in the transformer core are due to eddy currents. Eddy currents are induced in the core due to time-varying magnetic flux. These currents can be minimized by constructing the core with thin laminations, which offer high resistance to the eddy currents. Both types of core losses can be represented by a shunt resistor in the equivalent circuit. Therefore, the complete equivalent circuit, which has taken all types of losses into account, would look like this.